derivative control mode. So when you talk about the derivative control mode, just like the previous ones, this one changes the output of the controller at a rate proportional to the change of the error signal. And this change is caused by a variation in the measured variable, the set point, or even both. The derivative mode contributes to the output of the controller only when the error is changing. And for this reason, the derivative mode is not always used alone, and it is always used in combination with other modes. So in other words, we are saying that the derivative control, and that is why it is always referred to as pre-act. It does not change with the error, but it changes with the rate of change in the error. And for that reason, the step, we can look at it, we can look at the derivative mode in response to both the step and the ramp input responses, and then we see why we are talking of it not to be used alone. So we can talk about it having that. So let's look at the derivative mode, how it responds to both the step and the ramp input. So when you talk about the derivative mode with the step and the ramp input, we can represent this. So this is the output V. We can have the graph for the output V. Then we can talk of that to be 0. Then at this point, we can also have an error. We graph for the error. Again, 0. So here is 0. So we can have this. So when we have an output like that, when we have a ramp, we can talk of having a ramp. So there, in that manner. So this is a step input. So when you talk of a step input, when you talk of a step input, when it goes up, it gives that, and then when it goes down, it is also infinite downwards. So this is infinite, and this is negative infinite. Then when we have, can talk of a ramp. So for a ramp, it means that we are having an output like this. Then when it is going down, it is the same as that. So that one, of course, this is against time. That is also time. So that is why you can see that from this graph that we've drawn. So you can see that for a step input, it does not respond to a step input. It doesn't respond to a step input. So in that case, that one makes it not to be used alone, because for a step input, it will give an infinite output. That is negative infinity or infinity. So that is why it is always never used alone. As we had said earlier, it does not change with the error, but actually changes with the rate of change in the error. So that means that at every instant, the output of the derivative mode is proportional to the slope and the rate of the change of the signal. The step response, those particular step response indicates why the ideal derivative mode is not used alone. If you look at the error curve, it has got an infinite slope for a step change, and derivative mode must respond with an infinite change in the controller output. So if you talk about making the derivative mode in actual practice, then the response of the derivative mode action to rapidly changing signals is always limited, and this greatly reduces the sensitivity of the controller to the unwanted noise spikes, which frequently occur in actual practice. So we can talk about the figures. So we can talk about the figures of both ideal and the real or the practical derivative modes, and then see the differences and maybe do the analysis of their equations so that we can understand better. So we can talk of the ideal. In the ideal, we we can talk of the capacitor, CD there. Then we have this, and then we have a representation of the op-amp. Then here we have RD, that is the resistor. So here we have the capacitor, CD, then there, that one comes there. So of course the input is the error, while the output is V. So this is now the ideal. And for the practical, the one that is always used, practical, is in this case we have, we can talk of R1 here. R1 goes to CD. Then we have, that one is the op-amp. Then of course there has to be that junction. Then that one goes to RD. So what you can see is that another new resistance is added in the name of R1. And this R1 is always to limit. Its main work is always to limit, and is to limit the response to the step input so that we don't have an infinite response. So this is the practical. This is the practical, and this is the ideal. So let's look at the analysis of the equations for the derivative mode. So when you talk about that, then we can talk of the ideal differentiator. So we can talk of the time domain equation. Talk of the time domain equation. Time domain equation. So when you talk of the time domain equation in this case, then we can talk of the ideal differentiator. Ideal differentiator. So when you talk of the ideal differentiator, then we know that the V, small v, is directly proportional to the rate of change of the error, which we can talk of as TD, the error, over dt. When you talk of the frequency domain equation, frequency domain equation. So when you talk of the frequency domain equation, and that is for the ideal differentiator, then we are simply talking about V all over E is given as T ds. So it is simply getting the Laplace transform of that, where d dt will become S, and then that one, the small e will become capital E. So V over E is going to be T ds. Then we can talk about the frequency domain for the practical differentiator. So when you talk about that, if you do the analysis, so we can talk of the frequency domain equation for practical differentiator. So when you talk of the practical differentiator, then TF will simply be given by V all over E, which is equals to T ds all over S R 1 CD plus 1. CD plus 1. And in this case, maybe if you look at the other things will remain the same, like small v for the time domain output signal, capital V for the frequency domain output signal, small e for the error, for the time domain error signal, capital E for the frequency domain error signal. And then what will change here is that when you talk of the TD, RD, TD will be given by RDCD, which is what we refer to as the derivative action time constant in seconds. Derivative action time constant in seconds. And then when you talk of the various resistances, then R1 is the input resistance in ohms. R1 is the input resistance in ohms. Then RD is actually the output resistance in ohms. Then C, D is the input capacitance in farads. Input capacitance in farads. Input capacitance in farads. So basically that is what derivative mode of control is all about. So the additional term, that is 1 plus S1R, 1 plus, or we can say SR1 CD plus 1, is always used in order to limit the response that is produced by rapidly changing signals. So now we can start by looking at the combinations. We are going to look at the combinations of proportional plus derivative, proportional plus integral, and again we look at the proportional plus integral plus derivative, that is commonly known as the PID controllers. So let's start by looking at the first case, that is the proportional plus integral. So in this case, the integral mode is always combined with the proportional mode, and this is always to provide automatic reset action, which will eliminate the proportional offset. So the error that was caused as a result of proportional offset, or the error that existed in the proportional mode of control, will be eliminated by the integral control. And then the same proportional control will eliminate the oscillations that occur as a result of integral control. So it is always used in processes with the large load changes when the proportional mode, where the proportional mode alone is not capable of reducing this particular offset to an acceptable level. So the integral mode in this case will provide the reset action, and this is done by constantly changing the controller output until the error will be reduced to 0. So we can use the figures below to look at whatever will happen at the outputs when they are combined. So we are going to look at both the output signal and also the error signal, and in order to make a comparison of the outputs in this case. So if you look at this, then let's look at this one, the step response of a proportional plus integral. So we can talk about the step response of a proportional plus integral control. So what we are looking at, the mode of control that we are looking at is P plus I control, the proportional plus integral control. So in that case, we can talk about the output V. We can have our output V curve here. So this is output V. Then we have 100. We can talk of 100. We say that it is in percentage. Then we can talk of something like that. Then it goes up, goes that way, goes that way. So comes down, goes that way, comes down, then goes in that manner. So when you look at that, so in this case here, we are talking about integral response. Here we'll have integral response. Here we'll have, at this point, we are going to have proportional response. Here, we are going to have proportional response. We are going to have proportional response here. Can talk of here. Here we are going to have the duplication of both proportional response by integral mode at this point. At that point, there will be duplication of both the proportional, and then at this point, we are going to have proportional mode here. Here we are going to have proportional mode response. Here also, we are going to have proportional mode response. Proportional mode response. Here we are going to have, again, proportional mode response. And whenever we are talking about the ramp, we talk about the integral response. integral response there, and so on. So that is what we're going to have. So when we have the error curve for the same, so the error curve, so here we have the error, and in this case we can have the error, so we can have it in that manner. So in that case we are going to have something that looks like a step for the step. Then at that point, no response. Then we have that one, time. Of course, these ones are all against time. So that is the response of a proportional integral controller, of a proportional plus integral controller. So we said that the main disadvantage of integral mode is that it always increases the tendency for oscillation of the controlled variable, and the gain of the proportional controller therefore must be reduced when it is combined with the integral mode. And when this is done, it reduces the ability of the controller to respond to the rapid load changes. So that is what we have. So maybe we can look at again at the analysis of the equations for the proportional plus integral. So we are going to start by looking at maybe the block diagram for the same proportional plus integral. So the block diagram for proportional plus integral, that is what we are going to start by looking at. Then we look at the analysis of the various equations. So in this case we can have a block diagram with R1 here, then here the junction, then from there we can have Ri, which is now going to be the output resistance, then we have Ci, then we have that, then representation of the op-amp in that manner, then this one comes to that, then we have the output, of course, output here is E, and then it's V not E, then the input here is E. Then that is now what we have for this case. So we can now look at the various equations that we can talk about. We are going to start by looking at the time domain equation. Time domain equation. Time domain equation. So for the time domain equation, small v, which is the output for the time domain, we are going to have Ke plus K all over Ti integral or between 0 and T E dt plus V naught. So that is the time domain equation that we are going to have. So when you go to the frequency domain equation, we are going to get the Laplace transform of this and then maybe rearrange it. So in that case, we are going to have the frequency domain equation. Frequency domain equation. So for the frequency domain equation, we are going to have V is going to be given by Ke plus into K all over Tis, then the whole of that one is multiplied by E. And then you can reorganize the same to get the frequency, no, not the frequency, but rather the transfer function. Transfer function. So if you get the transfer function of this, then transfer function is given as output over input, that is V over E, which is going to be given as K into Tis plus 1, and then all over Tis. So those ones are the equations that you can use in order to carry out an analysis on the P plus I control mode, that is proportional plus integral control mode. And of course, these ones, the representation still remains the same, small v, the time domain, output signal, V naught, time domain output signal, when at t is equals to 0. Then we also have capital E, frequency domain, output signal. Ti, in this case, Ti will be the same as Ri over Ci, which is the integral action time constant. Maybe additional thing that we can look at is K, which is now given as the output resistance, which is Ri, all over the input resistance, which is R1. And you can also see that Ri in this case is the output resistance in ohms, while R1 is the input resistance in ohms, while Ci will be the output capacitance in farads. So that is what we can talk about. So here again we can look at another simple example that we can work on, we can try to solve, and then we move forward to other modes of control. So let's look at an example in this combination. So the question is determine the values of R1 and Ri. So the question is, so we can talk of example, determine the values of R1 and Ri for an electronic proportional plus integral controller, for an electronic proportional and integral controller with a gain in bracket K of 2 and an integral action time constant and an integral action time constant, an integral action time constant into bracket Ti of 50 seconds, full stop, use 10 raised to power negative 5 farad capacitor for Ci, full stop, determine the time domain equation, and the transfer function So in this case, we are looking at this. So what we are supposed to start by looking at is that we should have vast knowledge about the equations that we are going to use. So the first thing that we are going to look at, we can look at the value of both Ri and R1, and that one we can look at it from the equation that we talked about, Ti. So we can talk about the equation from Ti is given by Ri Ci. So we don't know what Ri is, but we are given Ti, and Ti is 50 seconds. So we can say 50 seconds will be given by Ri times Ci. We have been given Ci, which is 10 raised to power negative 5. And therefore, Ri is the same as 50 divided by 10 raised to power negative 5. So if you do your calculations properly, you are going to get 5 times 10 raised to power 6 ohms. 5 times 10 raised to power 6 ohms. So that is the value of Ri. So after obtaining the value of Ri now, you can use the other equations in order to obtain what R, the other R. So from the equations that we had talked about, we found out that K is given by Ri over R1. So we can use that in order to get R1 because we've already obtained Ri. So from the equation, we can say that from the equation, from K is equals to Ri all over R1, we can now find, we know that K is given as 2, that is 2 is going to be Ri, that is Ri is given as 5 times 10 raised to power 6, then divide by R1, then it simply means that our R1 is going to be given by, 5 times 10 raised to power 6 divided by 2, which is 2.5 times 10 raised to power 6, again in ohms. So that is now the value of R1. Then when it comes to the time domain equation, we are simply going to write it the way it is and maybe give the values that are there. So the other equation that we've been asked is the time domain equation. So when we talk of the time domain equation, we know that from the time domain equation, our V, the first part is that it is, because we are talking about proportional plus integral, the first part is that it is directly proportional to the error, while the second part is that it's directly proportional to the integral of the error, and that is between 0 and t, e dt plus v naught. So in that case, the representation of this, we have the value of k, so we simply take the values that are available and put them. Of course, there are some values that we are not going to have, like the value of e and v naught, and therefore we are going to express the equation just in that manner. We don't need to wind it up. So in that case, our small v is going to be k, which is 2. It's going to be k, which is 2, e plus k again is 2, ti is over 50, integral of between 0 and t, e dt plus v naught. And with that, you shall have obtained the time domain equation. So if you want to obtain the other question that we've been asked is the transfer function. So if you want to obtain the transfer function again, there are some values that we will not have. So generally the transfer function equation we were given by v is given as ke. The transfer function is v all over e is equals to k into tis plus 1 all over tis. So you simply put in the values. So v all over e is going to be given by k is 2 into tis, that is 50s plus 1 all over 50s. So with that, you shall have solved what you want to obtain, especially if you are asked about obtaining the transfer function. So for more examples, again, you can make a quick reference to EES.education so that you can see further examples on the same.